Yes, I just noticed your time.
Okay. Okay, thank you. Yeah. Okay. So I'll continue for a little bit, and I want to spend the next 15 or 20 minutes talking about an example of a very, very challenging parameterization problem we decided to tackle a few years ago. And that is one of a molecule called cobalamin. So this is actually, comes in different forms. In this case, this is cyanocobalamin. This is vitamin B12. So it's something that we have to get from our diet, or in some cases, if you have like pernicious anemia, maybe have to supplement to get enough B12. Okay. And so what cobalamin is actually this very complicated molecule with a metal center, a cobalt, in fact. Cobalt is particularly interesting because it actually forms a covalent bond with a carbon. And that's why it's in particular so useful as a nutrient within us, because it gets used, for example, for the building of the sheaths of our nerves and so on. And it has very interesting chemistry, but then that also makes it extremely challenging to simulate accurately. Okay, so here's chemical structure. So again, I mentioned there's a cobalt center. You have this corin ring around it. You see the 4 nitrogens that coordinated there in the middle, and then a number of associated attached moieties to it, as well as this base down here that comes underneath. Okay. So how do we go about parameterizing this? Well, first thing you look at it, you cry, and then maybe say, okay, I'm gonna switch to a different project. Yeah. But okay, we decided we really wanted to understand this, and there are a lot of interesting proteins that make use of this, so we thought it was worthwhile. Okay, so the first step, well, it's kind of tedious, but we gotta name all the atoms. I mean, there's tons of carbons and stuff. So, okay, somebody very carefully and painstakingly puts a name on each atom, okay, and make sure it's a unique name. So, all the way from, I see C, what's the smallest one? Well, I see C10 or C9, yeah, the C's, all the way up to like C60 or 60 something, okay. Okay, so tedious, but you got to do it. And then if you're so inclined, you can make a nice ASCII image of it too. You don't have to. Remember, that's in a comment in the topology file, but it's very helpful, right? Because if somebody else wants to come along and use it, that ASCII image is a great way to know, okay, where is C54? Oh, okay, that's this one right. Well, where's my pointer? This one right here, So you don't have to do it, but it's very useful in the long run. Okay, so how do we parameterize this? So first of all, it's too big for it's about on the order of 100 atoms. This is realistically, this is too big for a lot of QM tools out there. It'll be really slow, or it may never converge. And in fact, we probably don't even want to, even if we could, because there's some, we talked about transferability before, this idea that the parameters should be transferable between different situations. So if we try to do it all at once, it's actually limiting in a sense, because you see like all these side chains sticking off, they're going to be flexible, and you don't want to necessarily develop parameters for only one conformation of those. So we'd like to break it up. And so, for example, that corin ring there, we may start with that separately. Like that's going to be pretty rigid, not too flexible. And so we'll do that. And then the side chains we may do separately, or may even take from existing parameters. And then, for example, this base down here, we will also do separately, noting the fact that it can take on very different conformations. And so we don't want to develop parameters that only apply to one conformation of it. Okay. So this is a choice we have to make, though. And unfortunately, I can't give you rules for how to do that. You have to use some chemical intuition, or if you don't have, like me, poor physicist, you go to the chemist next door and say, hey, how would you break this up? Like, what do you think are the important regions to focus on? Okay. Okay. And then we actually, but again, Chris asked about, doing this all ab initio from start to finish. We don't do that, though. We want to lean on what's already out there. And so we use a tool, a web server now it's called CGenFF, used to be called ParamChem. This is a tool from Alex McCarroll, who is the main developer of the Charm force field. I just yesterday, in fact, I went in, they updated their website, so I grabbed the latest snapshot of the latest version. And so what this server does, it's not doing any parameterization for you, to be clear. It doesn't do any QM calculations or anything. What it does is, by analogy, compares the chemical description or the chemistry of your molecule to ones that already exist in the force field, and then gives you as close a parameters as it can find. Okay, so these will be of varying utility, but as we'll see, sometimes that can be good enough even for your purposes. So we don't want to rederive things that already are covered in the force field pretty well. One thing to note, this is the way a lot of things are going. It's free for academic use. So if you don't have an EDU address, you may be in trouble. Okay. And if you're in industry, you have to negotiate with them separately to use it. Okay. Okay. So you go there, there's some, you click, okay, you log in and then click parameterize. And then you get something like this. So I just uploaded a molecule L-DOPA just as an example. Now, one thing to note, for whatever reason, they want for a good reason, they want a mol2 file, because remember, PDBs don't necessarily store bonds. They don't want to guess it for you, because they think, okay, if we guess it wrong, you're going to blame us. So like, you tell me where the bonds are. And so one way to do that is to use a different type of file called mol2. It's like a PDB, it stores coordinates, but importantly, it also explicitly stores bonds as well. VMD can write mol2 files. If you go to your TK console and you make a selection and you say selection write mol2, it'll give you a file, but at least I don't know how to force it to put the bonds in there. But there's a tool within VMD called Molifacture that if you load your molecule in VMD, then you open Molifacture, and then there you do write mol2, it will store the bonds. Okay, so that's your kind of quick shortcut way of getting a file that you can then upload to this CGenFF server. And then you upload it, it shows you just that you can confirm that it looks as you expect, and then you click the Run CGenFF engine, and it will give you some parameters. Okay. One thing to be careful about, remember it said it was free for academic users. Make sure you're logged in, or you're going to get something like this. It says cost to run job, this small molecule, $350, please. Okay. But if you're academic, logged in, you'll be fine. It'll be free. Okay. Yes, I got logged out, and then it was giving me this, and then I was like, oh crap, does it not work anymore? It's like, oh, okay, I just had to log back in again. Okay.
I believe you.
Yeah.
But for some reason, it's like just a bit of educated guesses. That's very expensive. You must be very educated.
It's pretty good. It's pretty good. I don't know if $350 is good, but it's good. Okay. So it gives you a parameter file. All right, it actually gives you a combined top par file, topology and parameters. And so we're just looking at the parameter part of that file. No, sorry. I apologize. This is the topology part of the file. And you see, okay, topology, it has atom, name, type, partial charge, and then exclamation point. Remember, exclamation point means comment. Everything after that's a comment. So what are those numbers there? Those are penalty scores. Okay. So you want to pay attention to these. So low penalties mean the parameters are really good. So even though it's by analogy, it's good enough, and we would just use those. High ones, not so good. And so the rule of thumb at least from the CGNFF folks, is that less than 10, reliable. Don't worry about it. Good enough. 10 to 50, maybe, you know, depending on how much time you have, maybe you think it's okay, but be cautious. And then greater than 50, it's basically, okay, we had to give you some number, but we do not trust it at all. And you'd better do some optimization using a tool like ffTK. Okay. So that's kind of the rule of thumb for the CGNFF. So sometimes you'll put in your molecule, if it's like a simple organic molecule, you may have low penalties for everything. And then you say, okay, we're good to go. Yeah, Raphael.
That penalty for keeping from charge, right?
This is charge, yeah, but there are penalties. I'm not showing it right. There are also penalties for the parameters, your bonds and angles and stuff. You also need to look at those. Yeah. Somebody, yeah.
So if the charge has low penalty, but bond has high penalty.
So you don't have to worry about the charges. In fact, they say here, charge penalty 142, so it's telling you the max, so that's this one. And param penalty, although we're not showing it, the max is 271 in this case. You just keep the partial charges and only do the bond and angle step of the in ffTK. Yeah. Yeah. Other questions. So we don't want to reinvent the wheel. You can, but it's really not worth your time, right? If by analogy it's telling you the penalty is really low, you can trust that it's good enough. Okay, for those. And then of course the ones that are high you have to worry about. Okay. So, okay, looking at our cobalamin, again, we're already breaking it down now into a simpler and simpler form. In particular, like cutting off these side chains, they just add complexity for our QM calculation, and they're pretty simple chemical moieties. So like this will be, if you plug this into the CGNFF web server, it will give you low penalties for these. So we can just take them, typically we can take them from the CGNFF and then cut them off for our ffTK optimization. Okay. So we're really only focusing on this core ring now, and possibly what's bonded to the cobalt. We keep like one part of the molecule that comes underneath in order to get that bonding with the cobalt correct. Okay. Still pretty big. It's on the order of about 50 atoms, so it's still very challenging for the QM. And it's challenging for a few reasons. One is that we don't even have an atom type for the cobalt. So kind of implicit in everything I've been saying up to now is that the atom types already exist for your atoms of interest. And that means that the atom type means it comes along with some Leonard-Jones parameters, that 612 potential we looked at. So in this case, cobalt, we didn't have that. So we did something really clever that comes, not clever by us, but clever by Alex Macaro, using something called a helium probe, where you have a helium atom and you look at the potential energy interaction, or the interaction energy as that helium atom approaches your new atom, in this case, our cobalt. And the reason this is useful is because the helium, right, is a noble gas, so it only interacts via Leonard-Jones, right? And so that's how you can separate that from every other interaction in your system, and then fit that energy to get the Leonard-Jones 612 parameters for our cobalt atom. And like I was saying, you know, previously, you know, talking about like interactions, in the charm force field, you use Hartree-Fock or MP2, 631G star basis set. So they're all fixed. When we're talking about metals, we have to do something different, because it's really, they do not handle metals well with these lots of d orbitals and such. So we also had to try different QM methods, like DFT methods like B3 lip and so forth. Okay. So what about the water interaction? So, you know, I said charm force field, we'd see how the interaction energy between and distance between the water molecule and each potential hydrogen bond donor to get the partial charge, or donor or acceptor. But now I got this cobalt buried there at the center. You know, I try to bring a water close to it. It can't get there. So what do I do? Okay, so again, we we make choices, right? We relax. We don't stick to a fixed paradigm. So we actually used, even though we're doing charm style parameters, we used RESP. We fit the electrostatic potential, or we tried to use RESP, but for the cobalt, it was unphysical because it's just too buried. So even RESP couldn't work. So we came up with a hybrid approach. We used something called natural population analysis. This is within the QM code that you can, it's a way to kind of assign the partial charges, NPA. And we did that just for the cobalt and the nitrogen atoms buried at the center. And then we used RESP for the atoms around it. So again, we're completely coming up with our own novel procedure here, but we had no choice because the existing procedures just weren't good enough for a molecule of this complexity. So the lesson is basically the recommended approaches can and often will fail. Don't be afraid to experiment.
So this works with, but it is still using the charm force field for the rest of the system.
Yes, yeah. So we're trying to follow charm, but noting that we can't in every case, and so you have to break from it.
Violating some.
Yeah, violating. But I mean, if you talk to like Alex, for example, I mean, they would probably say the same. Alex and others would say the same thing, that you just have to sometimes break from the orthodoxy a little bit. Yeah. Be a little unorthodox. Okay, so we also had to, I'm kind of glossing over the bonds and angles, at least in this case, those were relatively straightforward, but the dihedrals, as they often are, pretty challenging. One thing to note, we don't always have to get a perfect fit everywhere. And so in particular, note this is energy on the y-axis. So we don't try to fit the high energy region so well, but we do want to fit the low energy region. So you can see here, the red is the starting, the blue is the final, and the black is the QM. And you see how we get really, really close within less than half a kcal per mole here in the low energy region. But the high energy region, we're still off by 1 or 2 kcals, but we don't care because Boltzmann sampling, those high energy regions are going to be exponentially less likely to be visited anyway. So fitting those is of exponentially less importance compared to fitting the lower energy regions. And so actually in ffTK, there's even a threshold you can make. This is a setting you can choose where to fit below and not fit above. Okay. We actually, so there's a lot of dihedrals in the ring there, like you can see all around the cobalt. We actually set a lot of them to 0 because the ring, because it was essentially would have been overfitting because you have so many bonds and angles in there. It's already well stabilized that adding extra dihedrals is just going to essentially be noise at that case. But again, this is a choice one has to make after reading the literature and thinking carefully about the problem. Okay. For the imidazole, again, thinking about because it's a planar ring, we only fit the even terms, n equals 2 and n equals 4 for our dihedrals. And it took a lot, and this was not a one shot. This was a case of multiple rounds of trying, fitting, testing, and then going back. But the end result was really, I was blown away by this. This was work by Anna Pavlova in my lab. And I mean, this Corin ring has very interesting structure that it's not totally planar. It's got little bends here and there. And the parameters are almost dead on. Like you see, even every little bend here in this ring was captured for the different charge states of the cobalamin. So the valence of 3, 2, and 1, it got them all perfect. So it can be done. Okay. Yeah, so minimization produced excellent agreement with the QM. Okay. And so this is my last slide. So of course we want to take those parameters we develop and put them into practice in the MD. So this is actually, it's kind of hard to see, but this is a cobalamin. It's actually this base that comes underneath is now unfolded, so that happens sometimes. And this is in this enzyme here that makes use of it. So it's PDB5C8A if you care. And so we monitor in the simulation, we monitor some different distances, we ran it multiple times, and we look essentially at how reasonable they are. And generally, they were pretty stable over 10 nanoseconds. You see one kind of jumped up here, but there we expect to have some fluctuations. We didn't think this was like necessarily a problem. So kind of showing us that our parameters are pretty reasonable. Okay. Okay, so that was glossing over. I mean, this is really, to be fair, I did this in 10 or 15 minutes, but this is a months-long process. But this is probably one of the most complicated molecules you'd ever have to even consider. Normally, it should be a few days process, maybe a couple of weeks, depending on how detailed you want to be. Okay, okay, so I'm done now. Any more questions? Yes.
So in the case where you start with the crystal structure, you take the, you take molecule out, do the geometry optimization, generate force field parameters. Is it necessary to put that optimized geometry back into
No.
the protein, or generating the force field parameters will correct that?
Right, the idea is that because, for example, this is not, the optimized geometry is in isolation. So this is in the context of interacting with the protein. So you should not expect the geometry to be the same. But hopefully your force field parameters are sufficient that it thinks it's a reasonably stable state. Yeah. Other questions?